Have you ever stopped to think about what's happening behind the scenes on a platform like LeetCode, especially during a huge real-time coding contest? It's way more than just a website with some problems. It's a high-performance system built to withstand an absolute storm of code submissions. So let's pull back the curtain and see how it all works.
Okay, picture this. A big contest just kicked off. You've got 10,000 developers, fingers on the keyboard, ready to go. And within just the first few minutes, they all smash that submit button. So what happens? Does the entire site just freeze? Does it all come crashing down? Honestly, this one question is the key to understanding the entire design.
And we're talking about some serious numbers here. We're looking at something like 200,000 code executions in just a 2-hour contest. If you do the math, that's an average of 27 submissions firing off every single second. Handling that kind of constant pressure without dropping a single one, well, that's the real engineering puzzle we're going to solve today.
So to really get a grip on this, we're going to keep it simple. We're just going to follow one single piece of code. We'll trace its entire journey from the moment you hit submit all the way to that beautiful, beautiful accepted message popping up on your screen.
All right, first up, the Contenders Challenge. This is all about that initial moment, that massive, insane spike of submissions. How in the world does the system absorb that tidal wave of traffic without completely breaking a sweat?
You know, the really tricky part here is that the traffic is anything but steady. Not even close. You get these enormous peaks, especially in that first minute of a contest. The number of submissions can be way, way higher than the average. If you just had a simple server, it would be toast. It'd get completely overwhelmed and just start dropping people's code on the floor. So how do you solve a massive traffic jam like that? Well, the secret sauce is a really elegant idea called a message queue. Just think of it like a digital waiting room. When that huge flood of submissions comes in, they don't just slam into the system. Nope. They get into this nice, orderly line, and the system can just pull them out one by one at a pace it can actually handle. And the most important part, no submissions get lost, and the whole thing doesn't just melt down.
Okay, so we've survived the initial flood. Now let's really dig in and trace the actual path our little piece of code takes. This is the core of the whole operation, from your browser to the final result.
It's basically a 4-step dance. First, the API gets your code. Step 2, it immediately shoves it into that message queue we just talked about. Then, a totally separate thing called a worker grabs your code from the queue and actually runs it. And finally, back on your computer, your browser just keeps checking in or polling to see if the result is ready. This separation of duties is absolutely crucial.
And this right here, this is the big idea behind asynchronous design. The system doesn't make you sit there and wait for your code to run. Instead, it takes your code, hands you a little receipt, that's your submission ID, and basically says, "Got it, I'm on it. Check back with me in a sec." This frees up the server immediately to help the next person, which is what makes it possible to handle thousands of users at once.
Okay, so our submission is waiting to be executed by a worker. But this brings us to a huge and kind of scary challenge: security. How do you safely run code that you're getting from thousands of complete strangers without letting them accidentally or intentionally burn down your entire infrastructure?
You've really got two ways to go here. There's the easy but incredibly reckless way: just run the code on your main server. But what happens when someone submits an infinite loop, or even worse, some malicious code? Poof, your whole system could go down. So the right way, the only way, is to use containers. Every single submission gets its very own secure, isolated execution chamber, completely walled off from everything else.
And we're not just putting the code in a box. We lock that box down tight. We put a strict limit on its CPU and memory usage so it can't hog all the resources. We give it a time limit so infinite loops just get killed. We even restrict what it can do on a system level and completely cut off its access to the network or the file system. It's a digital fortress, making sure one person's bad code can't ruin the contest for everybody else.
So the code has run, the result is in. How do we get that news back to you? You might think of something fancy like WebSockets, keeping a constant connection open. But just imagine trying to maintain 10,000 of those open connections. It would be a nightmare for the server's memory. The much, much smarter and more efficient solution for this scale is just simple polling. Your browser just politely asks the server, "Hey, is it done yet?" every second or so. It's simple, it's light, and it works perfectly.
So our submission was a success. You did it. You solved the problem. Awesome. But that one single victory sets off our final high-stakes challenge: updating that contest leaderboard for everyone in real time.
See, when you get a correct answer, it's not just about your score. It can instantly change your rank. And by doing that, it can shift the rank of every single person who was below you. Now imagine that happening hundreds of times a second during a busy contest. That creates a really interesting data problem.
If you tried to use a classic SQL database for this, it would just fall over. Every time someone wanted to see the leaderboard, the database would have to resort thousands and thousands of rows from scratch. It's painfully slow. This is a classic case of needing the right tool for the job, and that tool is Redis. Specifically, a data structure it has called a sorted set. The magic here is that it's an in-memory list that is, by its very design, always sorted.
This makes the whole process insanely fast. When a user's score changes, you use one command, zadd. And when you need to show the top 50 people on the leaderboard, you use another command, zriverrange. That's it. These two simple things are the powerhouse behind a leaderboard that feels absolutely instantaneous, even when it's getting hammered with updates.
Okay, time for a pro-level technique. We've talked about using a message queue to handle those submission spikes. But what happens in the biggest of the big competitions, where the spike is so massive that even the queue starts to feel the heat?
I'm serious. What do you do if the submissions are coming in so fast that your poor execution workers just can't keep up? The queue just gets longer and longer and longer. Sure, you could just throw 1,000 more servers at the problem, but there's a much cleverer way to handle it. It's a neat little trick called two-phase processing. Here's how it works. During the actual contest, you don't run the code against all the test cases. You just run it on a small sample, maybe 10% of them, just to give the user quick feedback. Then, after the contest is over, you go back and run everyone's final code against the other 90% of test cases to get the official final ranking. This one trick can cut the system load during that peak period by 90%. It's a game changer.
So let's just quickly boil this all down to the core principles. Number 1, decouple your system with queues to handle those wild traffic spikes. Number 2, isolate all that untrusted code with containers to keep things secure. Number 3, use simple polling to get results back to the user efficiently. And finally, number 4, always use the right tool for the job, like using Redis for a blazing fast leaderboard.
This is a super solid architecture that handles the scale we've been talking about. But, in system design, you're never really done. As a platform gets bigger and bigger, new problems, new bottlenecks always pop up. So I'll leave you with this to think about. If you had to make this system 10 times bigger, what do you think would be the very next thing to break? And how would you even start to fix it?